Morning everybody. Today I am going to tell you about a very interesting example of a two component system with congruent melting point. I have already told you about the zinc and magnesium system which was having only one component point. But what I am going to tell you about the ferric chloride water system, and it is having 5 eutectic points and 4 congruent melting points. So come on, let's start with it. So this ferric chloride water system, it is actually a two component system. The one is the ferric chloride and another is the water system. And you can see on the board, this seems to be a bit complex, but in fact it's very easily understandable and very interesting also. So we take ferric chloride and water, and as you all know, these two axes, they will represent our temperature abscissa, and this is for the composition. This composition I have taken regarding per 100 moles of water, and ferric chloride is being added continuously. So you can see over there, and rest I will explain to you later on. So actually ferric chloride on reaction with water, it will form 4 stable hydrates, and those are ferric chloride, dodecahydrate. Dodeca means 10 in Latin, and do means 2. So dodeca means 12 molecules of H2O. So in fact we are taking double molecules of ferric chloride to compensate for the heptahydrate. Actually it is 3.5, to make it 7 heptahydrate, we will be taking double molecules of ferric chloride. So one is the dodecahydrate, one stable hydrate is dodecahydrate, the second stable hydrate is the heptahydrate, ferric chloride heptahydrate. Third stable hydrate is the pentahydrate, means 5 H2O molecules are there, and the fourth stable hydrate is the tetrahydrate, means ferric chloride FeCl3, and there are 4 H2O molecules associated with it. And one of the phase will be the anhydrous ferric chloride, and one will be the water and water solution of ferric chloride, since we will be mixing the ferric chloride in water. So one will be that unsaturated phase and one will be the ice phase. So in all there will be 8 phases, and it is a two component system of ferric chloride and water. So let's get started with it. The first point I would like to tell you about is A. So this is 0 degree centigrade, and you all know it is the freezing point of water, or we can say melting point of ice. So A represents the freezing point of water, the melting point of ice, and this curve AB, this represents the freezing point of water to which more and more of ferric chloride is being added. So when we add ferric chloride to it, the freezing point of water, or you can say the melting point of ice, it is getting lowered with the addition of ferric chloride till point B is reached. And at point B, what we have is ice, and at point B, we will be having ice. And what will happen? A stable hydrate, dodecahydrate of ferric chloride, will also start appearing over here. So we have the ice, I will represent dodecahydrate by 12 H2O, 0.12 H2O. So we will be having ice, we will be having dodecahydrate, as well as the unsaturated solution of the ferric chloride. So in fact there will be 3 phases over here in equilibrium at point B. So this is our first eutectic point, which corresponds to a temperature of -55 degrees centigrade. You can see here I have represented all the eutectic points temperature, and here I have represented all the congruent melting points temperature for your easy understanding. So this point, this is represented by 2.75 moles composition of ferric chloride and -55 degrees centigrade temperature. And we can see in this phase diagram that -55 degrees centigrade is the lowest temperature that can be attained over here. Okay, and it is also known as the cryohydrate point, eutectic point as well as cryohydrate point. So this is our first eutectic point, and this curve AB, this the freezing point curve of water, to which continuous quantities, small quantities of ferric chloride are being added. Now comes this curve BC. Actually BCD. It represents the solubility curve of dodecahydrate of ferric chloride. And the curve BC, this represents the solubility curve of dodecahydrate in water. And we can see till point C, this represents the congruent melting point of dodecahydrate. We are getting a solution richer and richer in ferric chloride till point C is reached. At point C, we have a liquid composition and a solid composition. We will get liquid as well as solid composition, which have the same composition. The liquid and the solid component will have the same composition. Means it will be a one component system at this point, because the phases, there will be two phases. One will be with the liquid dodecahydrate, another with the solid dodecahydrate. And both these phases will have the same composition. So it will be a one component system at point C. This is our first component melting point also, because if we cool it a bit, we will get a solid of the same composition as that of the liquid. So this is our first melting point, first congruent melting point. And at this point, this corresponds to 37 degrees centigrade temperature and composition of 8.33% moles of ferric chloride. This is our first congruent melting point. Okay. Now comes the curve C. Yes, let me tell you about the degree of freedom over here at this point C. We will have to apply the reduced phase rule equation, which is given by F dash equal to C minus P plus 1. And since the number of components over here is only 1, the number of components is 1, but the number of phases are 2. So if we apply the reduced phase rule equation, F dash equal to C minus P plus 1, then F dash will come out to be 0. You can calculate that. So F dash comes out to be 0 over here. This means that the system is non-variant or invariant at this congruent melting point C. Now comes the point, the curve C. This represents the melting point or the freezing point of dodecahydrate, to which quantities of FeCl3 are being added. Till point D is reached, it becomes saturated in ferric chloride, and till point D is reached. At point D, what happens? Another stable hydrate, a heptahydrate of ferric chloride starts separating. So at this point, the three phases which are in equilibrium are, first is dodecahydrate. I am representing it by 12H2O dot 12H2O. You can understand the rest. So 12H2O, this is one of the phase. The another phase will be the heptahydrate, which is getting separated over here, and another will be the unsaturated solution of ferric chloride. So in fact, three phases are here. Let me write that also, solution. So three phases are here, and if we calculate F dash over here for a two component system, when we calculate F dash over here, that will come out to be 0. This means that this our second eutectic point corresponding to a temperature of 26 degrees centigrade and the mole fraction of something, it must be between 8 and 14, and mole fraction of this much, I think it is 12%. Yes, 12. So the mole fraction of 12 and a temperature of 26 degrees centigrade. This will correspond to our second eutectic point, and the degree of freedom here is 0, means the system is non-variant at this point. Okay. Now we are having these three phases over here, but the most remarkable feature is the appearance of the heptahydrate over here. Now what will happen when we dissolve more and more of ferric chloride to it and we heat it? What will happen? This this will show us the solubility curve of our heptahydrate, and heptahydrate goes on dissolving in it till a point E is reached. Now E is another congruent melting point, and at this point, if we cool it a bit, we will have a solid heptahydrate and as well as the liquid solution of heptahydrate. If we cool the liquid solution of heptahydrate, we will have a solid phase of exactly the same composition as that of the liquid one. So the solid and liquid are again having the same composition, means it is a one component system at this point E. One composition, but the phases are two. One is the solid heptahydrate, another is the liquid heptahydrate. So if we calculate F dash over here, that will come out to be 0, and 0 means the system is non-variant at the point E, our second incongruent melting point. First one is this, second one is this, second incongruent melting point. So now let's come over to this curve here. We are having the heptahydrate over here, and this will represent the melting point curve of heptahydrate, to which more and more of FeCl3 are being added, and it goes on decreasing till point F is reached. Till the point F is reached. And at point F, what will happen? When there are actually 15.12 moles of ferric chloride has been added till now. So what will happen? Another stable hydrate, the pentahydrate, will start separating out. So what we have over here is, there will be three phases in equilibrium, one being the heptahydrate, another will be the pentahydrate, and one will be the solution. So again, we are having three phases. Actually, this is the unsaturated solution phase over above all these curves. So that I have written over here just for easy understanding. The three phases which are will be the heptahydrate, the pentahydrate, and the solution. These three phases will be in equilibrium, and if we calculate the degree of freedom over here, F dash is equal to C minus P plus 1, then F dash will come out to be 0. This means that the system is non-variant at this point, our third eutectic point. So this will be our third eutectic point, first being B, second is D, and this is our third eutectic point. Now comes this curve GF, and we can see that it is the solubility curve of pentahydrate, to which would be dissolved into water, because here is the water with which more and more water is added. We see GF will be the solubility curve. So what will happen if we consider this empty, more and more of this H2O, 7H2, 5H2O, 7H2O will start disappearing and 5H2O will be there till a point G is reached. What will happen at point G? We will be having a solid form of, if we cool it a bit at this temperature, means 56 degrees centigrade, if we cool a bit, we will get a solid phase of this pentahydrate. Means here we will be having two phases, the solid pentahydrate and the liquid pentahydrate. They both will be having the same composition. They will be having the same composition, and means there will be only one component at this point G and two phases. And when there are two phases in one component, and if we apply the reduced phase rule equation, then again the degree of freedom will come out to be 0. This means this point G, our third congruent melting point, will be invariant or non-variant, since the degree of freedom is 0. Now comes the composition. You can see it's 20, means 1:4, 1:5 of water. Okay, 20 mole percent, 1:5, and the temperature corresponding to it is 56 degrees centigrade. I have mentioned the congruent melting points over that portion of the graph, and all the eutectic points at this portion of the graph, just for an easy understanding. So now we come over to this curve GH. So this curve GH, it represents the freezing point curve of pentahydrate of ferric chloride, and this goes on decreasing, the freezing point goes on decreasing till point H is reached. And at point H, what will happen? We will be having not only pentahydrate, another stable hydrate, the tetrahydrate of ferric chloride, will also start appearing over here. So what we have is the pentahydrate, the tetrahydrate, solution of the. So the three phases will be, these three phases will be there, and if you calculate average, that will come out to be 0. Come to this curve HJ. Actually, if we see JH, it will be actually the solubility curve for tetrahydrate to which water is being added. But if we see like this HJ, this is actually, we are having this phase is appearing over here, the tetrahydrate, and at this point it will get concentrated with more and more addition of ferric chloride. It will get concentrated, and a point J will reach when we will have a liquid. If we cool it a bit, we will get a solid phase of the same composition as that of the liquid. Now another, this will be our fourth congruent melting point, because we will have a stable hydrate which on cooling will form a solid state of exactly the same composition as that of the liquid. This means we will be having a single component over here, but there will be two phases, the solid and the liquid phase, and the component will be one. Again, if we calculate F dash over here, that will come out to be 0, means the system is non-variant at our fourth congruent melting point. So this one was the first, second, third, and this one is our fourth congruent melting point, corresponding to a temperature of 73 degrees centigrade and mole composition of 25%. Mole composition means roughly, not roughly, exactly 1:4 ratio of with water. So this was about the point J. Now comes our curve JK. So JK represents the melting point curve or the freezing point curve of this tetrahydrate of ferric chloride. And as we can see, the freezing point decreases with addition of more and more of ferric chloride, and comes the lowest point K, at which now anhydrous ferric chloride will start separating. So at this point K, we will have three phases, and this is our fifth eutectic point of this ferric chloride water system. So the three phases which will be in equilibrium at this point are actually the tetrahydrate of ferric chloride, anhydrous ferric chloride, and the saturated and the unsaturated solution of ferric chloride. So these will be our three phases which will be in equilibrium at our eutectic point K. And since three phases are in equilibrium, if we calculate the degree of freedom over here, that will again come out to be 0, means the system is non-variant at this point K. So now we are left with one more curve LK. This represents the solubility of the anhydrous ferric chloride. This point LK represents the solubility of anhydrous ferric chloride. So this was all about the ferric chloride water system. I think it was quite understandable and very interesting also. It is having 5 eutectic points represented by B, D, F, H and K, and there are 4 congruent melting points represented by C, E, G and K. You can all note down the temperatures, the molar compositions of ferric chloride. I have written all these the compositions and the temperatures of the eutectic as well as the congruent. You can note it down, and that's all for this ferric chloride water system. And in my next video, I will be telling you about a very interesting feature, that is the isothermal evaporation of an unsaturated solution of ferric chloride in water. That makes a very interesting study, and we can study that from the phase diagram very easily. Actually, that will be the isothermal evaporation of ferric chloride of unsaturated solution of ferric chloride, and we will see how the phases change, how the hydrates change with the isothermal evaporation. Evaporation is done at constant temperature conditions. So thank you very much for this, and the link for this isothermal will be given in the description box of ferric chloride water system, and the ferric chloride water system link will be given in that description box of the isothermal evaporation of ferric chloride and saturation solution of ferric